So let's go back to the original question. So this is kind of what compressibility is basically how does things like density or volume change as changes in pressure. Of course, the pressure itself, as we will see, will change as a result of changing the flow conditions. In this case, we are changing the Mach number. So let's look at some typical physical aspects in the flow field as we increase the flow Mach number. So what I'm showing you here is a typical subsonic airflow, which is basically in a flow field of free stream Mach number. So the free stream Mach number here is M1. I know we usually use M infinity. We're just using M1 here. So in your case, this is basically the Mach number you guys were asked to look at, whatever that's subsonic, transonic, or supersonic. So that's your Mach number there. So this airfoil is typically at a small angle of attack, and we're not going to change the angle of attack, and we're not going to change the airfoil. The only thing we're going to do is slowly increase the Mach number M1, and then see what happens, what kind of flow field we might have. This is the question, which again is very similar to your, in a way, similar to what you're doing in your coursework. So yeah, that's the question. So what type of changes in the flow field, including the forces and moment? Now, the changes I'm going to discuss with you, don't think these are kind of, they're always like this, because obviously they might depend on the geometry of the airfoil or the wing, the particular conditions, the angle of attack we started with, and so forth. So although the general behaviors kind of are okay, don't take them, they have to be always that way. Right, so let's start with a relatively low subsonic Mach number, M1 equal to 0.65, right? In this case, typically for a subsonic airfoil, we don't really see much. So the flow goes around, there is not really, the only thing you might see towards the trailing edge is a small separation region causing a small wake behind the airfoil, okay? So of course, as we know, the way to generate lift is that the flow speeds up on the upper surface and slows down on the lower surface, generally. Okay, so initially, typically for this Mach number, for this airfoil, remember it doesn't have to be for all airfoils. Some airfoils might have slightly different flow field for this particular Mach number, but this is illustration. Anyway, so initially everything is subsonic. So this is subsonic. You will find that the flow around the airfoil itself, locally, top and bottom, is also subsonic from the trailing edge from the leading edge trailing edge. Now we move from 0.65, let's say, to 0.75. What you will see as the speed increases, then the speed up effect on the upper surface and the slowing down on the lower surface will increase, which means you're actually increasing, you're getting more lift. So you guys can see from 0.65 to 75, clearly there's nothing yet, there's no shock waves, but surely as you increase the speed, you should get more lift. And if you look very carefully here, I know it's not very well drawn, but this is actually meant to be the lift coefficient as a function of Mach number here, which is as a function of M1. So as you guys can see, as we increase the Mach number, initially the lift will increase, okay? So it will just go up. As I said, that's because of the speeding up effects on the upper surface and slowing down on the upper surface. So you're creating more pressure difference as usual, okay? Right, in terms of the drag and the moment, we have a small note here saying if you look at the drag stays more or less constant. It actually increases very, very slightly, but in the realm of things, it's kind of more or less constant, as does the moment. So for these low subsonic flows, the lift increasing, but the moment and the drag remain relatively constant. So these are the main observations we can make. So now obviously we want to go beyond 0.75. So let's see what we can get. So M1 now is 0.81, right? So you guys immediately see in the picture to your right is there's something on the upper surface of the airfoil. Well, for a start, the local Mach number m is greater than 1. So although the free stream Mach number is less than 1, clearly, it's subsonic, the local speed on the upper surface is greater than 1. So this is a supersonic region, although the wing itself is flying subsonically. And in fact, it's quite a sizable region, really, on the upper surface. And all this region here of supersonic flow ends with a shock wave. Okay, and that shock wave is typically a normal shock wave. Okay, so you guys can see is more or less the shock wave is sitting more or less normal to the surface. Okay, on the lower surface, we're not seeing, there is nothing really yet. Okay, the exciting changes, the supersonic flow is actually only on the upper surface. There is nothing yet on the lower surface. Okay. Remember I told you if you have a normal shock wave, then the Mach number behind it should be subsonic. So in your case, if you do a particular case, and you see and you plot a contour of Mach numbers, and you will see that it changes from supersonic to subsonic, most likely probably have a normal shock wave. And actually, if you plot things very well, even the shape of the shock wave will look more or less normal, if that's what it is. But before talking about the shock wave, there is something called the critical Mach number in aerospace. And that critical Mach number is basically defined as, I think I have a definition on the next slide, if you don't mind. I'll come back to the slide. So before actually having the shock waves and that supersonic region over the top surface, let's just define the critical Mach number. What is the critical Mach number? So the critical Mach number is the free stream Mach number, okay, at which somewhere on the wing there will be the first appearance of supersonic flow, even at just one point. So if one point on the wing where the flow has reached m equal to 1, okay, at that free stream speed where this happens, that's called the critical Mach number. For example, I don't know, take a Boeing 777 flying at 0.75. It could be that the critical Mach number when we say the critical Mach number for the Boeing 777 is 0.75, it means at that 0.75, somewhere on the wing of the aircraft, there must be a region, even if it's just a point, where the flow has locally reached supersonic flow. It doesn't mean you will have definitely a shock wave, but at least there is even a very small region of supersonic flow. And that's what the critical Mach number is. It's basically where the flow locally is starting to become supersonic on the wing. Okay? But of course, remember, we're defining this critical Mach number as a free stream Mach number for the aircraft. Okay? So if I go back here, so if I ask you in the exam what is the critical Mach number, I do expect you to know how to do that. So M1.81, okay, so I told you there is already a region of supersonic flow. And typically here, in this region of critical, in this free stream Mach number, the critical Mach number is typically between 0.7 and 0.8. Okay, I'm not sure what type of airfoil you guys are using, but in general, critical Mach numbers for a lot of the airfoils these days is put between 0.7 and 0.8. Okay, so clearly here in this case, I'm already at 0.81. There is already a large region of supersonic flow, which means actually the critical Mach number is actually lower than 0.81. But just remember, the critical Mach number is the instance where for the first time there is supersonic flow on the wing, even without a shock wave. Okay, so what happens? So we are 0.81. If we keep looking at the lift coefficient, so 0.81, maybe we are here. So the lift is still increasing. Okay, there is a normal shock wave. On the bottom surface, there is nothing, and it actually happens, apparently, that for this particular airfoil, around 0.8 itself, the lift coefficient reaches a peak. Okay? So that's kind of, that will be the highest lift coefficient achieved by the airfall. Let's say around 0.8, okay? And of course, because we have the shock wave, the first thing you guys need to think about is the fact that you have a shock wave, you must have what we call wave drag. So suddenly the wing is kind of struggling, okay? So the wave drag, once you have the shock waves, is actually appearing there. So we can't ignore, remember I told you before the drag is slowly not increasing, but now we have the shock wave, definitely there will be an increase in drag. That's called the wave drag. If we look at the moment, typically it's still, even at beyond this critical Mach number and at the highest lift and the drag is increasing due to wave drag, it's actually still relatively constant. Okay. So now, so what we do, we're going to keep increasing the Mach number beyond 0.81. So let's see what happens. So now it's 0.89. We're approaching Mach 1 slowly for the speed of the aircraft. Now, if you do that, now is quite interesting because, first of all, the supersonic region on the upper surface has become bigger. So it actually spreads over a larger area of the upper surface. So if I go back here, hopefully you guys can see that. So this is the region here at 0.81. If I go 0.89, that supersonic region has actually increased in size over the upper surface, which actually, and remember, the supersonic region always ends with a shock wave. So that means the shock wave we have seen previously has now moved more towards the trailing edge, as you guys hopefully can see, right? Can you see that? So the shock wave in the upper surface has moved more towards the trailing edge. Now, interestingly, now there's something also on the lower surface where actually we also have supersonic region, m greater than 1, on the lower surface as well. Again, any supersonic region must end with a shock wave. So in this case, the shock wave on the lower surface is just towards the trailing edge, or very close to the trailing edge, sorry. Right, so you got really two shock waves in this case. Now, what could also happen physically is something called shock stalling. And basically what is shock stalling is the shock wave, if it's strong enough, it will cause the boundary layer to separate. Now, remember guys, flow separation is one of the enemies of flight. We don't want flow separation because that will give us a lot of pressure drag, or what we call pressure drag due to flow separation. So, and actually, I can tell you that in terms of research, there is a huge research into kind of shock wave boundary layer interaction. And people are still kind of doing a lot of work trying to understand how the shock wave affects the boundary layer, okay? But one of the things that could definitely happen is definitely the shock wave being strong enough and it causes the boundary layer to separate. Now that's not very good news because first of all you have the shock wave and the wave drag, and now you created even a bigger problem by causing the boundary layer to separate. So that's kind of, if you are in that situation, obviously that's not very good for your airfall. Right, remember guys, I told you that previously here we've reached a kind of a maximum for CL at around 0.8 Mach number, right? So what you guys can see after that is that the lift coefficient actually reduces. So it reduces after 0.8, around 0.8. So in this case, but it's still less than 1. So as we go above 0.8, the CL is going down, and it goes down to a minimum point here. Now the reason for that is, if you guys look at the pressure distribution on the top and the bottom, is that, remember, to generate more lift, you have to have very high pressure on the bottom, low pressure at the top, or high suction at the top. What's happening here, unfortunately, is we have supersonic flow here and supersonic flow here. So if you guys think about it in terms of the pressure difference is actually getting less because even the bottom surface is now supersonic flow, is very fast as well. So this is what causes the reduction in lift. And so this is why we see the lift coefficient going down with supersonic regions like this. So we spoke about shock stalling, the reduction in CL. Right, in terms of the pitching moment, if you look at the pitching moment, this sudden decrease in the lift, okay, might cause a sudden change in pitching moment. So if you were a pilot and you got this something like this on your wing, you might feel a sudden pitching moment. Then obviously you have to operate the elevator to get out of that, either nose up or nose down, depending on how the pitching moment is feeling. So in this region here, there is a sudden change in pitching moment. I think these are the main, kind of the main observations you might see for your airfall. Okay, so Mach number is 89. Actually, we're going to increase it even further now. Okay, let me actually just very briefly talk again about boundary layer separation due to shock wave. So when you have flow separation, you get, the flow becomes so turbulent. So you get a lot of eddies, and those eddies are basically lost energy, which means your engines must work hard to account for that. And one way to think about separation is just think about it as a wake behind a boat or any body. So it's an unsteady phenomena, and the pressure drag increases due to flow separation. So as I said, in real life, it means you have to put extra power from the engine to deal with that. But also there are structural problems. So when you have flow which is separating, with time, it causes vibrations on your structure, particularly the wing, and that's of course not a good thing for your wing. So there are penalties in terms of the drag, there are penalties in terms of lift, but are also penalties in terms of the structure itself. Now, apparently, in rare cases, the flow separation due to the shock wave becomes so violent and so kind of huge and important that pilots have reported not being able to control the aircraft due to sudden flow separation. It's almost like operating in a stall, right? Any pilots here who have done stall, who are brave enough to try stall? You did it. How did you come out of it?
The rudder.
You used the rudder. Okay, that's interesting. So, honestly, tell us. Fascinating. So, did you feel the sudden loss in lift? What happens? You went. Okay. So, all right, interesting. Why the rudder? Can't really. Okay, but you obviously were able to come out of the stall because you're still alive. But anyway, this is actually a very serious problem for aircraft, all right? But luckily, these are rare cases, and obviously, any respectable corporation developing aircraft, obviously, they must have think about these issues and not allow them to happen. Probably these issues happen on maybe business jets or something, but they're rare cases, luckily. Anyway, let's go back to increasing the Mach number, the free stream Mach number. So now we're very approaching the Mach 1. So not quite Mach 1, but 0.98. So what you guys can see now that, okay, the shock waves, upper and lower, are actually exactly at the trailing edge, which means both surfaces, lower and upper, are completely supersonic, okay? And they end up with shock waves. However, if you guys look very carefully at those shock waves, then now, are they normal shock waves? Do you guys think they're normal shock waves? Are they normal, or would you treat them as normal shock waves, or not really? They're oblique shock waves, right? So they become oblique shock waves. So, so what happens then is, so we are in this region now. So remember, the lift coefficient went down, and then now it's increasing again to it starts increasing. Just before 1, it reaches, it actually reaches this second peak around just before 1. So it's probably around this Mach number as well. So it goes down to a minimum and then starts reach again, and then after that it goes down. So these are the main characteristics. So the first thing is top and bottom is supersonic. Any supersonic region must end in a shock wave. The shock wave are exactly at the trailing edge now. They're both oblique shock waves. Okay. In terms of what's happening to the drag, so I'll show you the drag curve in a moment. But actually, if you look at the drag curve as we approach Mach 1, it actually will reach a peak value itself. So the drag is keep increasing and actually very close to 1. This is kind of your worst enemy in terms of the drag. Right. In terms of pitching moment, people have found that if you measure the pitching moment, let's say quarter chord, it becomes more negative. Before it was positive, now it's more negative. It's kind of the other way around. So it's a pitching down, is a nose down pitching moment. Right. So let's keep going, see what happens. Finally, this is just a case of the free stream number now, the free stream Mach number is above 1. Okay? So we were just before 1, and then we went to, let's say, 0.14, sorry. Right, what could happen in this case is quite interesting things. So again, we still have the bow shocks from the upper surface and lower surface towards the trailing edge. Okay? Now, the first thing what's appearing here is this bow shock in front of the airfoil, right? So which we didn't have before. Okay? In supersonic flow. So you have this bow shock. So remember I told you guys, if you have a bow shock, the flow behind the bow shock must be subsonic. So again, in your, I don't know, has anyone found this in their CFD runs? You found it. And it's definitely the flow is subsonic behind it. Good. So that makes sense. So which means you must have a bow shock. So if you have this case, the flow behind it here is subsonic, and then it becomes supersonic on the upper and lower surface, and then they both end with shock waves like this. Again, these shock waves are oblique shock waves. And in that case, what you guys can see is the CL reduces, actually reduces after that. Okay, and again, if we trace why the CL is reducing, we need to look at the pressure coefficient. So remember here is both the upper and lower surfaces, they're both kind of supersonic. Obviously, to get some lift, there will be more suction, so lower pressure on the upper surface compared to the lower surface. But that difference is small, okay, because they're both supersonic, and that gives you less lift. So it's interesting that at low Mach numbers, as you increase the Mach number, you get a huge increase in CL. After that, it drops, rises again, and then if you go supersonic, the lift goes down again. So it's very interesting to kind of bear those changes in mind. Now, the existence of bow shocks like this and these shocks at the trailing edge, this is what causes what we call the sonic boom, the bang that we hear as the aircraft goes through Mach 1, right? So these shock wave system is what causes that bang that we hear. So, in terms of what's happening to the drag, I'll show you in a minute what happens to the drag. But the drag, apparently, the CD reduces, okay, as we go towards this Mach number, although the drag itself continues to increase. In terms of the pitching moment, apparently the pitching moment at around this Mach number reaches again a constant value. But of course, you guys can see the lift is decreasing continuously as we go higher Mach numbers above 1. So I would say these are kind of the main changes that you might see as you increase the Mach number. They're not universal changes, so please don't take these slides as kind of you know, this is what can only happen. No, they might depend on your shape of your airfoil and the conditions you started with, like angle of attack and so forth. But this is kind of some of the things that can happen. And what you guys really should be looking for is, first of all, how do you identify a shock wave from your runs? And whether that shock wave is a normal shock wave, is an oblique shock wave, and whether that shock wave type that actually makes sense in terms of the lift and drag you're looking at, in terms of the pitching moment, and so forth. So try to relate what you see in pictures, whether that it makes sense in terms of the moments and the forces as well. Of course, we can't describe everything, but hopefully I've given you some of the things to think about. So in terms of summary, we can just take summary like this as the Mach number increases, you know, from low speeds to high speeds. I've given you here, this is a typical curve for the lift coefficient. As I said, increases, so you get more lift at low subsonics. It reaches a peak at around, let's say for this one, let's say around 0.7, and then it goes down to a minimum before 1, goes up again, reaches a maximum just before 1, and then after 1, then it goes down again. So this is a typical, if I ask you a question, could you draw a typical behavior for the lift coefficient of an airfoil as we go through, as we increase the Mach number from subsonic to supersonic? This is a general shape that is true for most wings. But of course, the points at which these maximums and minimums occur, they are dependent on your shape, of course. All right, but this is a general kind of shape. So if you couldn't, by the way, I realize, yeah, I was able to get these pictures, but if you don't find these pictures very clear, so probably they're not the best, I put them here again so you can look at them kind of separately, right? Right, let me describe the drag, because obviously the drag is a very important thing in aircraft design. So, how does the drag look like as we increase the Mach number? What is the general shape for that? So, here is how it looks like. So we have here on the y-axis the wing drag coefficient, and here is the free stream Mach number. Okay, this is the free stream Mach number, i.e. the speed of the aircraft, if you like. So what we said is at low Mach numbers, you will find that the drag coefficient is actually more or less constant. It's not actually strictly constant, but in relative terms is more or less constant. So we're increasing right at a certain point, or a certain Mach number called the critical Mach number. Remember I told you the critical Mach number is the free stream Mach number at which locally on the wing there is supersonic flow. And at that point, once you have supersonic flow, you need to start thinking about wave drag. And this is why at the critical Mach number, after that, the drag increases. Why? Because there is possibility of shock waves forming, and shock waves cause wave drag. So the drag starts to increase. If you look very carefully, it actually increases, it starts increasing, but then it reaches another Mach number where the increase is suddenly very steep. And at that point where the increase is suddenly goes steep, that's actually called the drag divergence Mach number. It's just from the name, the drag itself diverges upwards suddenly and very, very highly. So that's called the Mach divergence, the drag divergence Mach number, sorry. So there are two Mach numbers there, the critical Mach number and the drag divergence Mach number. So the critical Mach number is the Mach number where the drag starts to increase because of possibility of shock waves. And after a small distance after that, actually, you also encounter the drag divergence Mach number. That's the Mach number at which there is a sudden increase in the drag, like as you guys can see. But it all happens, all of these changes, they happen before Mach number of 1. Okay, so this sudden increase in drag is actually before Mach number 1. And exactly at around Mach number, this is called the sound barrier. Historically, this is where basically people, actually, believe it or not, at some point before, people never believed they could fly faster than the speed of sound. So there was a myth, if you like, that we can't fly faster than the speed of sound. So that's why the kind of the sound barrier came from, which is basically Mach 1. So it reaches a peak around Mach 1. So you guys can see, you can learn straight away from this graph that actually flying exactly at Mach 1, it's not really a good idea. Okay, you're very fast, but you're really flying at the maximum drag that you can have. And that's because of you're going through the sound barrier. Anyway, after that, interestingly, actually, the drag coefficient drops down, which is good news as you go with, but it's still quite high, of course, compared to subsonic, okay? Still quite high. And in relation to what I told you before, you can get the shock waves may become oblique at high enough Mach number. So if I go back here, so these are oblique shock waves here towards the trailing edge, okay? So there's still quite, the drag is still quite high, and you might get oblique shock waves. So this graph, I want you to think very carefully about this graph because it's actually quite important in terms of aircraft design. So we know the shape is like this, and I put something at the end of the slide saying, what is the design philosophy for transonic wings, for wings that fly close to the Mach number 1? What's the design philosophy, just based on the drag curve? Well, clearly, we don't want to, this increase in drag will happen at some point for your aircraft, okay? So the aircraft is speeding up. Of course, you want to fly faster, but you will be limited if this drag rise suddenly occurs. So clearly, what you guys want to do is you want to push the speed higher before that increase in drag occurs, right? Clearly. So you want to kind of push this curve here to the right so you can fly faster and you delay the increase in drag. Right? Is everyone clear? Logically. And that's actually historically what people have been doing. So they thought about various ways really to push either the critical Mach number or the drag divergence Mach number further, closer to 1 if possible, so that this drag rise is delayed. Okay? Simple as that. Because once you have this sudden increase in drag, basically your aircraft is being slowed down. Okay? So it's kind of being pushed backward by the huge increase in drag, and your engines must, of course, provide more power to that. Okay, right. I think these are the main points. Now, this slide, it just summarizes all what I said about the drag, variation of drag. This is, again, the general drag curve I've just shown you here. So you can have a look at it again if you want. This is just, again, don't worry about, you can have a look at this or this, but really this is just what we said is the pitching moment at low Mach numbers is relatively constant. After that, it starts to change, okay, into +1, and then -1 as we go beyond Mach 1. So kind of these are the main changes in pitching moment. Which, of course, pitching moment always think about it in terms of aircraft stability and control. Because once you have a pitching moment, your aircraft is unstable, and you have to correct for that. The drag is to do with the thrust, and of course the lift is to do with sustaining the flight and everyone in the aircraft, of course. Right. Some of the things just to remember. So we can remember the problem of shock stall, please. That's a very important problem, okay? So basically the shock wave is so strong, you get boundary layer separation. That increases your drag. Remember, your lift is not high at those conditions, so the L over D actually becomes low, okay? And also, the changes in the sudden increase in drag and the change in the pitching moment, okay? Which obviously make our flying difficult. There is a rapid increase in drag towards 1, as we showed you here. So as you approach 1, Mach 1, you guys can see there is a huge increase in drag. This is why transonic is so kind of annoying. It's quite exciting, but actually we still don't understand it very well, to be honest. What's happening that causes all of those is actually still, part of it is not well understood. But we know from experience, yes, there is a lot of drag. So flying very close to 1, you know, it's not a very good idea. Or you can do it, but you're going to have to pay a huge drag penalty.